So today we're going to be solving trigonometric equations. Now there's several ways to look at these and several ways to solve them. We're going to walk through three different ways to do them. The general rule for solving a trig function is we're going to try and isolate the trig function in and of itself. Once we've isolated that trig function, then we take a look at what method we want to use to actually jump into it. So let's go ahead and we're going to start out with number one. Now, number one, we have this graph off here to the side that we're going to be looking at and consulting. The first way that we can solve this is by consulting the graph and saying, when is my sine of x equal to 1/2? Well, here's my graph of sine of x, and 1/2 is going to be equal to roughly there on the graph. So I'm going to go ahead and draw a horizontal line all the way across and say, hey, I get a point right here, right here, right here, and over there. So I've got 4 values that I can see. I also know that this graph keeps going on to the right and it keeps going on to the left, which means I'm going to have several more iterations. So I need to figure out what this value is. I see the fact that I'm probably going to be repeating myself at this value, and this downward trend is going to repeat itself over here. So I'm going to pull out an actual helper so we can draw this. So I am going to set up our function. So I know the sine of x. Sine is going to be the y over the r value, which means my graph that I'm representing is going to be some unknown angle measure is going to give me a y value of 1 and a radius of 2. And I should recognize that that 1, 2 is going to be over root 3 because it is a 30, 60, 90 triangle. Now that 30, 60, 90 triangle is going to help me get my first round of answers. I know that x is going to be equal to 30 degrees, or if I want to put that in radians, pi over 6. And then because I've seen the graph and I know that it repeats itself, I know that sine repeats itself every period or every 360 degrees. If it was radians, every 2 pi radians. I know if that happens once, it's just plus 360. But it can also happen at 720 or 1080. Same thing with radians. It happens every 2 pi, every 4 pi, every 6 pi. So the way that we show that is we put a k in front of it. What this tells us is that it's 30 degrees plus some number of 360s, whether that be 1, 10, 1,000, or -5. It doesn't quite matter. So that's round 1 of the answers. Now, what we also notice is that sine is positive both in, let's take another quick look at this. I know sine is positive both in the first quadrant and in the second quadrant. So I should have not only my first graph right here, which is in the A area, but I know that the sine is also positive in the second quadrant, which means that this graph happens again. And if I know this is a 30, 60, 90, well, I know that that must be 150 degrees because I know that the straight line is 180. Take away the 30, and I'm left with 150 degrees. So when I come over here, I know that that point must be at 150. So 150 degrees plus some iteration of 360. If I write that as a radian, I know 150 degrees as radians. Let's see, that would be 6 over 6 pi. So 5 over 6 pi. And then I'm going to go ahead and put a k in front of that to signify that that is my second round. Now let's say we didn't quite remember how to set up those functions. There is a slightly different way that we can figure out what the sine of x equals, or what the x equals to make sine of x equal to 1/2. And I can type that into my calculator using an inverse trig function. So I could say sine to the -1 of 1/2 is equal to x. And now most calculators have this exact script. The problem is that with this negative 1 right here, that does cause a little bit of confusion. So most people, when we write it by hand, we write it in what we call Arcus notation. And so we'll write it as arcsine of 1/2. These effectively mean the same thing. Now, because the script of this is a little confusing and not everybody uses the arc sign, some people just simply use the sign to the -1, you'll get some people that refer to this as still an inverse trig function, but they capitalize the s to separate sine to the -1 from the inverse of sine, which would be the cosecant function. Because this is not sine raised to the -1, this is saying the inverse of sine, meaning this is the ratio of sides, and it will produce therein an angle. This is the angle that will produce a ratio of sides. But regardless, whichever way you write it, if you plug this into the calculator, you'll get one of two possible answers. If you plug in 1/2 sine -1, you will get an answer of 30 if you're using degrees, or you'll get an answer of 0.52, which is the equivalent of pi over 6. So you'll get that first round and you'll get part of the answer, which will be all you really need to graph the rest of this. Well, I know, hey, if this is 30, I know where this is. I should be able to go 30 degrees back from that. There we go. Let's try one more. That was kind of a lot to digest there, so let's take a look at another one. This is cosine. So I'm going to be doing the same approach. If I wanted to do this, let's say simply by the calculator to get us started, and I'm like, you know what, I don't even want to look at the graph. I want to simply look at what can I type in. I'm going to write this in inverse trig notation. So that's going to be the cosine -1 of root 2 over 2. I could also write this in arcus notation, which is arc cos of root 2 over 2. Or I could write this as capital cosine of root 2 over 2. Any of which will make my x equal, and let's take a look at what that would be. So let's see. I would go ahead and plug in my inverse cosine of root 2 over 2. And I'll get 45. And because the mode is in degrees, I know that's going to be 45 degrees. Or if I were to write that as a radian, pi over 4. And now let's take a look at what that would mean if I used this graph to represent that. Well, I'm asking when is the cosine of x equal to root 2 over 2? Well, I know that root 2 over 2 is somewhere between 0 and 1 because I know that the root of 2 is somewhere between 0 and 2. So I'd actually have to say, okay, well, what is the root 2 over 2? 0.7. So somewhere about 7/10 of the way up, I want to find that. So I know that I want to find this decreasing or this decreasing slash increasing or increasing. I know this is what looks like if that is pi. This is half of pi, which means that this is going to be roughly equal to half of that. So x is equal to 45 degrees plus 360 pi over 4 plus 2 pi k times. And I'd get part of my answer. I would get every answer marked with an x. What I wouldn't get is I wouldn't get the second value of the answer. Now, I know that if this is 45 degrees forward, that must mean that this is 45 degrees to the left. So I'm going to have to either go over here and say, well, this is -45, or I could say this is 360 minus 45, which will give me 315 degrees. Or, in this case, 7 pi over 4. Give our k to indicate that it's going to repeat that often. And now again, this is another version that doesn't necessarily rely on what exactly we're doing. So let's take a quick side approach and look at what exactly we just did right there. So we're asking ourselves with the cosine, which is x over r, when does that produce a value for x which produces the adjacent or the x value of root 2 over 2? Well, we should recognize this triangle because this is a 45, 45, 90 triangle. So I know that because of that, this is also root 2. I know that my x, not my x coordinate, my x value is equal to 45 degrees. And I'll be able to quickly figure out what the other angle measure is because I know with this indicator, for all students take calculus, I know cosine is positive both in the first and in the fourth quadrant, which means I'll have a second triangle, which will still give me root 2 over 2, which is going to be 360 minus that 45 degrees, which is 315. Boom. There we go. So either way you work it, we're going to end up getting the same answer. And so the next one, what I want you to do is I want you to take a quick pause and I want you to try out the tangent feature. Unpause it when you're done and see how well you did. Okay, so let's take a look at the tangent feature. And in this case, we're going to go back to approaching it via the graphical method. So if I have the tangent value of 1, I know the tangent is going to be equal to the y over x. I know that y over x means they're either both positive or I know that they could both be negative. So I'm going to go ahead and say, okay. And my tangent is going to be equal to 1, which means whatever they are, they're going to be the same thing. So why not just make it 1 over 1 or negative 1 over negative 1? This, I should immediately recognize that's isosceles, or I should get that this is going to be root 2, which is a 45, 45, 90 angle again. This is also 45, which means that this is going to be 180 plus 45, which is 225. I know that if given those, it's going to be every point around the unit circle at that value. Let's go ahead and answer our question. So x is going to be equal to 45 degrees plus the period of tangent is going to be 180. So pi over 4, and the period of pi, or the period of tangent is going to be pi. Boom. And that's all I need. Now, if I wanted to use my graph as a guide instead of drawing the unit circle, I could go ahead and say, well, when is the tangent of x equal to 1? Which means here, 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 and here. I notice that's the same type of intercept. Tangent's always increasing, which means that I know that my period should be a lot faster, and I'm not finding a second set of values to coordinate. The other thing is if I wanted to figure out what those values were, I could say, okay, let's plug this into the calculator as either the inverse tangent of 1, the arctangent of 1, or the capital tangent inverse of 1. All of which, when you plug them into the calculator, will give you an answer of 45, or pi over 4. Awesome. So let's see how we did. The last couple are a little different. So when I'm dealing with the cosecant of x, if I try and plug this into the calculator first, I'm going to end up with a problem because first off, most calculators don't have the inverse cosecant of an undefined number. First off, I'd be having problems trying to plug in an undefined number. I don't know how to type that in. So I wouldn't know how to make cosecant undefined if I can't type in undefined. But what I can do is I can go ahead and rewrite cosecant in a version we might recognize. Well, how about I write, instead of cosecant of x, I write 1 over the sine of x equals something undefined. And then I'm going to ask myself, well, what is an undefined number? Well, an undefined number is some number divided by 0. Hey, conveniently, I have some number divided by the sine. Why don't I actually just make, it doesn't really matter what the number is, so I can set it as any number, including the number 1. How about when is the sine of x equal to 0? Okay, well the sine of x is equal to 0 at the same point that my cosecant graph is undefined. So I see that my cosecant graph is undefined at x equals 0 plus 180, or 0 plus pi. So there's my answer. If I tried to relate it into something I plug into the calculator, I would rewrite it as the sine of x equals 0. So then I could either say sine -1 of 0, I could say the arc sine of 0, or I could say capital sine of 0, all of which would give me a value of 0. Perfect. And so the last two questions, we're trying to relate a graph that doesn't quite fit what we're working with here. So how would I relate y equals 2 sine of x to give me an answer to sine of x equals -1? Well, what I could do is, because I've isolated the sine of x in both these, I could make my given equation, let's say I'm given all the points along this graph, and so I'm using this as my resource. I know it's the sine of, or 2 times the sine of x. So I'm going to go ahead and double my value right here and say, okay, well, if that's 2 sine of x, let me just double the left and double the right. When is 2 sine of x -2? Boom, right there. I know that that is every time I hit a trough. So I know that my x is going to be equal to, let's see, 3 pi over 2. And 3 pi over 2 should be roughly 270 degrees, plus every period. So my period is 2 pi, and I'm going to pop a k right in there. There we go. So that's if I wanted to use the graph as a guide. Let's say I don't want to use the graph as a guide. I can do what we've done before, where I plug in the inverse sine of -1. That will always give you the first answer, which will either be the negative value right here or the positive value over there. So why don't you go ahead and try out the last one on your own. Go ahead and take the cosine of x plus 1 and use that to answer the graph of the cosine of x. When does that equal -1? Okay, now that you've had a shot at that, well, if I want to make cosine of x plus 1, why don't I just add 1 to my function? Cosine of x plus 1, if I add 1, when does that equal 0? Well, looks like that happens at x equals pi plus 2 pi, or every 180 degrees plus 360. Add my k for multiple iterations, and there we go. So that closes out the front style questions, which is going to bring us to our next set of problems. Now, these problems are more of the equation sense and less of the just tell me what the sines and cosines are, because we do need to work these just a little bit. So let's take a quick look at number 1. If I have the sine of x plus root 2 is equal to negative sine x, all I need to do at this point is go ahead and isolate the trig function as best I can, which means I'm going to combine these into 2 sine x plus root 2. Subtract my root 2, so 2 times the sine of x equals negative root 2. Then I'm going to divide by 2, so the sine of x equals negative root 2 over 2. Now, a couple ways I could solve this. I could solve this by saying, hey, what x values give me a y over this radius? Or what I could do is I could say, hey, let's get a good general idea of what's going on. All students take calculus. I know with the negative values, I'm dealing with 2 angles that are down here. So I'm going to have a triangle in the 3rd quadrant and a triangle in the 4th quadrant. I know that both of them are going to have a negative root 2, and a 2 as the hypotenuse. So let's go ahead and figure out what that x value is. So if I take the inverse sine of a negative root 2 over 2, I'll get negative 45 degrees. So x is going to be equal to negative 45 degrees. Oop, that's a degree symbol. Awesome. So that's really all I need to answer the rest of this. If that is negative 45 degrees, I know that they gave me this value. So my first answer is x equals negative 45 degrees plus 360 every k time. I know that that's negative 45. This is negative 180 plus 45. Or I can say that this is 180 plus 45. I'm going to go with the 180 plus 45. So x is also equal to 225 plus k, 360. Unless you wanted to do it in radians, which would be pi over 4 plus k2 pi, or 5 pi over 4 plus k2 pi. You can either do it in radians or in degrees. Doesn't really matter. Perfect. Let's do one more. Number 3. The procedure is the same. I want to isolate this trig function as best I can, which means 3 tangent squared of x is equal to 1. Move the 1 over. Move the 3 over is 1/3. And then I say, okay, I'm going to take the square root. So the tangent of x is equal to the positive or negative version of 1/3, which really says that this is the tangent of x is equal to the positive or negative 1 over root 3. So with this, I know if it's both positive or negative, I'm going to have an angle in all 4 pieces, which means I'm going to have possibly 4 different answers. But luckily, because tangent repeats itself every pi units, I'm just going to deal with the 2 answers. So real quick, let's go ahead and figure out what the tangent of 1 over root 3 is going to be equal to. So the tangent of 1 divided by root 3, so this is the positive version, is going to be 30. Perfect. So if x is 30 degrees, that means that I've got this as 30. I know the fact that I'll have that same ratio over here, which is going to be, let's see, 180 minus 30 is going to be 150 degrees. I know that it repeats itself every 180 degrees or every pi. Oh, every 180 degrees. I'd write this over here as pi over 6 plus pi. This one, well, let's see if that was 6 pi over 6. That is now 5 pi over 6 plus pi. And then it's going to be every k units. So I either have my degrees or I have my radians, whichever you prefer better. Now that you've seen 2 examples, why don't you go ahead and try out number 5. Number 5 is a little more complicated because we're going to have to do a little bit of rewriting before we begin, and this one might have to do with a little bit of factoring. So go ahead, pause the video, and pause it when you're done and see what you did. Okay, so let's take a look. The first step we always like to do with these is rewrite them as the cosine over the sine times the cosine squared is equal to 2 cosine over sine. Now I notice that they both have a cosine over sine, so the first step that I'm going to do is go ahead and move that over. Perfect. And now that everything's moved over, what that allows me to do is factor out a cosine over sine. So if I factor that out, I have 2 expressions. Now, the first expression is pretty straightforward, because what I can do over here is say, okay, the sine of x cannot be 0. So come over here. The sine of x cannot be 0, which means that the sine of x, in order for that to be 0, is going to be every x cannot be 0 plus pi units, because it's 0 twice every period. I could put 0 every pi units and then pi every 2 pi units, but we're just going to say, hey, as long as x is not part of these values, we're fine. So when is the cosine of x equal to 0? Well, now the cosine of x is going to be a couple different points here. Okay. So the cosine of x is equal to 0 every 90 degrees plus k 2 pi, or k 180 degrees. Or I could say, okay, if it happens there, it'll also happen. Let's double check. Okay, so it happened at 90. It's going to happen again at 270. If I want to write that in radians, I would say that is pi over 2 plus k, should be 360 right here, plus k2 pi, or I would say 3 pi over 2 plus k2 pi. I can do either one of those. The problem that I run into with this one is with my second value, and this is going to give me a non-real answer, or something that doesn't work. I know that the cosine squared of x is going to be equal to 2. I know that the cosine of x is going to be equal to root 2. I know because cosine is going to be the x over the radius, and I have a root 2 as the x and the radius of 1, that's saying that my x value is bigger than my radius, which means that one of the legs of my triangle is bigger than the hypotenuse. So this does not exist. Perfect. I have 90 degrees every 360 and 270 degrees every 360, as long as x doesn't equal that. And last but not least, we have a quadratic sine graph. So with this one, what I want to give you a piece of advice before I let you try it on your own is try and factor this like you would factor any other quadratic, but instead of solving for x, think of it as the sine of x, and see if that helps you out. So go ahead, pause the video, unpause it when you're done, and see how well you did. Okay. So I'm going to take that into consideration and say, hey, how about I treat this like a quadratic? So I'm going to say 2 times 1 is 2. It's a positive 2, so I'm taking the sum. 1 and 2 make 3, which means that I'm going to use those as my 3. So 2 sine squared x minus sine x minus 2 sine x plus 1 is equal to 0. Split my 3 into minus 2 minus 1. I'm going to pull out a sine x, and I'm going to pull out a negative 1, which means that sine x minus 1 times 2 sine x minus 1 are both equal to 0. So I get value 1, value 2. So when does the sine of x equal 1? And when does the sine of x equal 1/2? Well, the sine of x equals 1 at the peak, which we know happens directly at 90 degrees. Or it happens at pi over 2. So answer number 1. Answer number 2 is when does sine of x equal 1/2? Well, we've already answered that at least once. We know the sine of x equals 1/2 at either 30 degrees. Let's go ahead and set this up. so 30, where it's 1 over 2, or over here at 150. And it repeats it every k 360. Every k 360. Which is every pi over 6 plus k 2 pi, or every 5 pi over 6 plus k 2 pi. And there we go.